In this video on differentiation, we're going to look at the quotient rule. And there it is, and you've probably seen it before. But I'm just going to explain one way of deriving that. If you know the product rule, okay, we can treat this a bit like a product, because u over v could be thought of as u times v to the power minus 1. So I'm just going to say let y equal u times the function, so that's the function u multiplied by the function v to the power of negative 1. Okay, in other words 1 over v. Now if we treat it like a product, then we know that dy by dx, okay, would be equal to v du by dx plus u dv by dx. But in this case, when I say v, I'm referring to v to the minus 1. So it's v to the minus 1 du by dx, okay, and plus, and then I'm saying it's u, okay, times dv by dx. Now, if you differentiate something, a function, to the power of minus 1, it becomes minus 1 times that function to the power of minus 2 by the chain rule multiplied by its derivative, which is dv by dx. Okay, so I've just applied the chain rule to work out the derivative of the function v to the power minus 1. Okay, now I'm going to show you that this can be converted into the product, into the quotient rule fairly quickly from here. So what I'm going to do now is I'm just going to write that as 1 over v, okay, times du by dx, and over here I'm going to write this as 1 over v squared, or minus 1 over v squared, okay, times u dv by dx. Okay, now it's nearly there. We just now need to take this left-hand term here and multiply the numerator and denominator by v, and that will then give us 1 over v squared, okay, 1 over v squared times v du by dx, okay, and we've got a plus minus here, so we can just put minus, and then we've got 1 over v squared u dv by dx. Okay, and that's just about there, because if you look at that expression I've just written down, if I take out a common factor of 1 over v squared, then it does indeed give me the quotient rule. So it's 1 over v squared, okay, and then that is multiplied by, well, it's basically this, isn't it? v du by dx, v du by dx minus u dv by dx. Okay, and you can quite easily prove the product rule by from first principles, and that's one way of doing it. And from there, if you accept that, you can use this to prove the quotient rule. Okay, so we've done a bit of background work. There is the quotient rule proved. In the exam, you only need to be able to use the quotient rule and not derive it from first principles. So there it is. But I'm going to move on now to a couple of example questions. Okay, now in the first question, it says find the equation of the tangent to the curve y equals e to the third x over x at the point 3, comma, a third e. Now, you need to treat this as a quotient. You could actually do this as a product and treat the second function as 1 over x, or x to the minus 1, but we're going to do it as a quotient. So the derivative dy by dx, or just simply y dash, which is a standard abbreviation, y prime, for the first derivative, and that is equal to 1 over x squared. Okay, so it's 1 over the square of the denominator. Now we have to, in brackets here, start by doing v, which is x, times the derivative of the numerator, and the derivative of e to the third x is a third e to the third x. Okay, make sure your powers are clear and elevated from the main part of the function. Okay, and that is then, that's the v du by dx, and then I need to subtract the u, which is e to the third x, times dv by dx, which of course is just 1. Okay, and I tend to put the full working down at this stage in the same order as it appears in the quotient rule, and then I can start simplifying it. Okay, now I can maybe change this around and factorize it, and in fact I'm going to do that by recognizing I've got a common factor of e to the third x over x squared. So I'm going to take out the e to the third x from the bracket. So I have e to the 1/3 x. Okay, and that's all over x squared, and then inside a bracket I'm left with 1/3 of x minus 1. Okay, 1/3 of x minus 1. Now, it asks me to find an equation for the tangent. So I need to know what the gradient of the tangent is at the point 3, comma, a third e. Well, all I need to do is plug 3 into this equation and just say that let's write it down here. So at x equals 3, y dash equals, well, it's going to be 0, because it's going to be a third of 3, which is 1, minus 1 is 0. Okay, so it's just going to be 0. So it's an unusual question because the gradient at that point is actually 0. It's a horizontal, it's momentarily horizontal at that point. So I could still use y minus y1 equals mx minus x1. So I could say y minus a third e equals the gradient m, okay, x minus x1, but I mean there's little point in that part because that's obviously going to be 0 on the right. So therefore I'm left with the fact that y must equal a third of e. And that's the equation of the line. And that's a horizontal line, of course, because a third e is a constant. And we know it's a horizontal line anyway because the gradient is 0. And that's the answer. Okay? So slightly unusual question because, as it happens, the gradient is 0 at that point. Okay, next question. Now this is clearly a quotient. And we could apply the quotient rule in full to this. So let's do this one here in a different color here. So we've got y equals log x over sine 3x. And remember that when you have a situation like this involving trig in any calculus, it's always in radians. So I can say that y dash equals, okay, 1 over the square of sine 3x. So it's sine squared 3x. Okay. And that has to be multiplied by sine 3x, okay, times the derivative of log x, which is 1 over x, okay, and from that I've got to subtract, leave the log x alone, and this time differentiate the sine 3x to give me 3 cos 3x. Now I'm using some spacing there, okay, and a little dot, but if you want to be really clear, you can always separate these parts with brackets, okay, just to make your intentions absolutely clear. Okay, now that's unsimplified at the moment. Various things you could do with that. And I'm going to actually just try and tidy it up a little bit, because I've got this sine squared 3x to go under both of these. So I'm just going to rewrite it as 1 over x sine 3x. Okay, 1 over x sine 3x. Okay, that's supposed to be a sign there. Oops. Right. Okay, so that's the first bit, and then I can take away from that 3 log x cos 3x. 3 log x cos 3x, and put that over sine squared 3x. Okay. I mean, there's other ways you could do that, but I'm just going to put it like that for now and see if that helps us out. And what we have to do here is we have to find the exact value of dy by dx, the exact value. So we need to use the exact trig values and so forth, and anything with log we just leave as a log. So let's just put the values in. Now you should be able to work on this fairly readily now. So when x equals pi by 9, let's put that in. Okay, so x equals pi over 9. Okay, we can now substitute it in. So that implies that y dash is equal to 1 over, now we've got underneath here pi by 9, okay, that's x, and sine of 3 pi by 9 is sine of pi by 3, which is the sine of 60 degrees, if you like, which you should know is root 3 over 2. Okay, root 3 over 2. And then I've got to subtract from that 3 times the log of pi by 9. And you wouldn't be expected to know what that is. You can just leave it as log pi by 9. Okay. And that has to be multiplied by the cos of 3 pi by 9, which is the cos of pi by 3, the cos of 60, which is a half. Okay. And if you're thinking of it in degrees, and then that has to be divided by sine of 60 degrees, or sine of pi by 3 squared. Well, we've done that already. It's root 3 over 2, and if you square that, that gives you 3/4. Okay, so it's that over 3/4. It's okay, so it looks a bit cumbersome at the moment, but I'm going to tidy this up in a moment. So we just have to simplify this as best we can. Well, what I'm going to do is recognise, of course, if you divide by 3/4, you're timesing by 4/3. And similarly, this can become 18 over pi root 3. So that's 18 on the top and pi root 3 underneath. Okay, and then that gets rid of that sort of tower of fractions. And then over here, I've got to put the 4/3 on top. So I've got 4/3 times by, well, I've got 3 log pi by 9, 3 log of pi by 9. Okay. And that's also times by 1/2. So I can put that, I'll put that at the end for the moment. Okay, and I've got the 3 up there as well. So I've got the 3's cancelling out, the 4 and the 2's cancelling out there. Let's just do one more sweep through this and tidy it up. This can be rationalised, so times top and bottom by root 3. So it's root 3 over 3. 18 over 3 is 6. So it's 6 root 3 over pi. 6 root 3 over pi. Okay, with a rationalised denominator. Okay, and then we've got to take away from that, well, we're going to be left with 6, that's going to be 2 log pi by 9 if you tidy up all those fractions. 2 times the natural log of pi by 9. Okay, and that needs to go in a bracket at the end. Okay, now sometimes we need to put modulus signs or magnitude signs around that because it has to be positive if it's a log, but we know pi by 9 is positive, so we don't need to in this case. Okay, and that is a simplified expression for that answer. And it says find the exact value. Now you could argue that these are all exact values, but in the context of a question like that, you would normally attempt to tidy it up and simplify it to a fair degree. You certainly wouldn't leave it like this with these towering fractions. Okay, so that's the answer I would present for that question, and they're both using the quotient rule. Okay, hope that was helpful. Take care.